Hello everyone. So welcome to the video lecture series of Strength of Material. I am Dr. Gyanendra Kumar Christie, Assistant Professor, Department of Civil Engineering, SR University, Warangal. So today our subject of interest is column and struts. So, so what is column and what are the struts? So you might have seen here I have kept 5 images. So as a civil engineer, you might have seen these kind of structures everywhere. Wherever you go, you might have seen these kind of common structural elements. So the first image is, you can see this is the column in the airport. So this column is, you might have gone to that place. This column is in the Mumbai International Airport. You might have visited there. So you can see the architectural view of this column. So this column is also gives us that flexibility to design. Architecturally it can be aesthetically so beautiful. So the second image is an ancient column structure that is in your city of Warangal. That is one of the oldest city in India. The third structure, the third image, that is a under construction image. The column is a column built in the apartment, the modern apartment construction. So this fourth image is a steel structure where this I section is used as a column. And the fifth, you can see this is a truss piece where this inclined members can be called as strut. So basically what is column and strut? So columns and struts are the structural elements which are used in construction, that is in civil engineering field, and you can see these elements in automobile engineering. You can see in the field of aerospace engineering, which is basically subjected to axial compressive load. So what this column, what is the role of this column? Column is used to provide vertical support and transmit force to the structures below. So you might have seen the struts are also used to provide facing outwards facing supports in any orientations. It may be horizontally, it may be vertically, okay, it may be diagonally. Okay. You can see this orientation of these struts. They are basically used to design members that support roofs or other structures. So columns and struts, if you ask me in which material they are made with, so these columns and struts are generally made up of steels or concrete, or it can also sometimes it is made up of timber. So as I already told, they have been used in architecture since ancient times, such as you can see in ancient Egyptian architectures. As early as you may find it in 2600 BC. So the history of column is you need to go through this history of column. You may find in any textbook. Next, so what are the learning outcomes we are going to study in this? chapter. So you'll understand what are the usage of columns and struts in building constructions. So you will go through the fundamentals of columns and struts, what are the types of columns, what are the end conditions, then what are the theorem. There are two theorems we'll discuss here. So it's Euler's theorem for evaluating the critical load on the long columns. So we'll understand what is the concept of equivalent length of the column with the different end conditions, slenderness ratio. Then we'll discuss about Euler's critical stress. Then we'll discuss some problems related to the Euler's formula. In the last, you'll understand what is this Rankine's formula and its applications. So coming to struts, as I already told you that a structural member, strut is a structural member that is subjected to an axial compressive force. It may be horizontal, it may be inclined up, it may be vertical. But columns, the vertical strut used in the buildings of frames is called columns. And the uses I already have discussed that usage of columns and struts are used in buildings and bridges. So this is a column that is taking the compressive load. Struts are the maybe inclined, maybe diagonal, maybe horizontal. So you might have seen this kind of structure. This vertical member is called your column. This horizontal member is beam, and that member is supporting this beam and is connected between this beam and column is often called strut. So what are the classification of columns? So according to the nature of failure, we have three classifications. The columns are three types. One is short column, there is medium column, and there is long column. So you can find these classifications. When the length to diameter ratio is less than 8, we often term that we can call it as a short column. Or if the slenderness ratio is less than 30, we'll explain what is, we'll discuss what is slenderness ratio later in this class. So next, what is medium column? If the length to diameter ratio is between 8 and 30, so we can call it as medium column. And if the L by D ratio is greater than 30, we can call it long column. So what is short column then? So short column is where the length is so related to its cross-sectional area that failure occurs due to direct compressive stress. So in case of short column, the failure is due to direct compressive stress. So there is no role of bending stress. So here the bending stress is negligible. So what is the medium column? Similarly, the length is so related to its cross-sectional area that the failure occurs due to combination of direct compressive stress and bending stress. And long column, where the length is so related to its cross-sectional area that failure occurs due to bending stress. If you ask me, let us just consider this as a short column. So its length is so related to its cross-sectional area that if we are applying the compressive load on both ends, so it will reach to a point where it will directly cross because of that compressive load. So it is not going to bend, or there is no bending stress developed in this. So this failure will be due to direct compressive stress. So if you consider this as a long column, where the length is So related to its cross-sectional area, the failure occurs due to bending stress. So if we apply load, compressive load from both ends, so it will reach at a point where the column starts buckling at its center. So here the column becomes instable. So you can understand it easily here. So this is called buckling of the column. So in long column, the role of direct compressive stress is negligible. So then what is buckling failure? As we discussed that failure of the short column is due to crossing failure and failure in long column happens due to buckling, buckling failure that is. So what is this buckling load then? So load at which column just buckles, as I shown you that here if we increase the load on the both end, so a load a point you come, a particular load, the column will start buckling. That load is called buckling load or critical load or crippling load. So while designing this column, it is very important to understand and to calculate what is the buckling load of the column. So it has also seen that for long column, the buckling load is less than the crossing load. So if we see this in an experiment, look at the loading condition here. Both ends are pinned or hinged. By just look at this video, how this column buckles when the both end conditions and both ends of the column are pinned. So here both ends are hinged. So the load is applied for both ends. So now see how this column buckles at the center of the center. Look at the deflection, how it is deflected from its original axis. Look at the buckling, how it buckles in the center. So here is your force displacement graph. So up to a certain point, there is a displacement. Your load is increased, so displacement is also increased. But a point comes where the column starts buckling, where the load get reduced. There is no further increase of the load. I hope you understood this concept, the buckling failure. So here, another example of buckling. This is nothing but your railway track. So because of the thermal expansion in the railway track, so there is a possibility of buckling of this railway track, where the I section is used at the railway track. So another example you can see here, under the sea there is a hot oil pipeline. So similarly, because of this thermal stress, there is a chance of buckling of the pipes. Here is another example of buckling failure. This is a column in a building where the both ends are fixed and it just buckled at the center of the beam. Coming to Euler's column theory. So we understand. So we understood what is the problem. So buckling failure. So to predict the buckling failure of the column, there is a mathematician Euler's developed after several experiments. He developed an equation, he developed a theory where you can predict the buckling load of the long column, which is based on the bending stress. So he derived an equation for buckling load of long column based on the bending stress. So he also fixed some assumptions in the Euler's column theory. So the first assumption is initially the column is perfectly straight and the load applied is truly axial. So your column has to be perfectly straight and the load applied has to be truly axial. So the second assumption is the cross section of the column should be uniform throughout its length. So cross section of the column has to be uniform throughout its length. So third is the column material is perfectly elastic, homogeneous and isotropic, and thus it should obey the Hooke's law. So next assumption is the length of the column is very large as compared to its cross-sectional dimension. So here he is expecting that the length of the column has to be very large as compared to its cross-sectional dimension, so that the column will buckle after buckle due to the applied axial stress. And the next assumptions is the shortening of the column due to direct compression is neglected. Yeah, because if the column the length is so large as compared to its cross-sectional dimension, so when the load increases, so what Euler's theory is expecting that it has to be failed due to only buckling load or the bending stress. There should not be any direct compression. The failure should not be because of a direct compression. If it is there, it has to be so small as compared to the bending stress, so that the shortening due to the direct compression is neglected in that case. So next is the failure of the column occurs due to buckling column that we discussed. So coming to the sign conventions. So we can see there is a column, when we apply loads, when we apply the compressive load, so it will buckle either way. It may buckle like this. That means it may be deviated from the axis in this way, or it deviated in this way. That is, one is convexity towards its initial center line, or at concavity towards its initial center line. So that is a movement which tend to bend the column with convexity towards its center line. We'll consider this as positive, and a movement which tends to bend the column with concavity towards its initial center line, we can consider it as negative. So there are many end conditions for the column, but from the analysis point of view, from the experiment point of view, we will only consider four conditions, four end conditions. So from where one of it is both end of the column are hinged. So you can see from this figure, it is an experiment on a laboratory to analyze how the column buckles when both ends are hinged. You can see the deflection at the center of the column. So if we consider AB as the column and we are applying the compressive load P, because of that, there is a deflection at the center of the column, and the length of the column, let us consider A. So if you derive this, how it was derived this theory, so we'll just discuss one end conditions and we'll see how he's deriving that. So consider any section at a distance of x from the end A, and where the deflection is y. So at the distance of x, the deflection is y. There is a lateral displacement. So the moment due to the crippling load of this section would be, so what would be the moment at this section? Is it P into y, load into this displacement, and there is a negative sign, that is because of the sign convection. There is a concavity versus initial axis of the column, so there is a negative sign. So but we know the moment is EI d square y by dx square. So if you equating these two moments, so EI d square y by dx square is equal to minus EY. Okay, so if you bring it to the left side, so EI d square y by dx square plus P into y is equal to 0. So if you divide this by EI, so d square y by dx square plus P by EI into y is equal to 0. This is a second order differential equation. So if you find the solution, the general solution of the differential equation is y is equal to C1 cos x root over P by EI plus C2 sin x root over P by EI, where C1 and C2 are constant of integration. So how will solve this? So we'll just apply the boundary conditions. So what are the boundary conditions here? So the two boundary conditions. One is at x at a at point A, if x is equal to 0. So where the distance x is 0 and y is equal to 0. This is one boundary condition. Another boundary condition at B if x is equal to L and y is equal to 0. So these two boundary conditions we have to put in that above equation. So if you substitute this value in equation 1, what is at x is at A, x is equal to 0 and y is equal to 0. So the equation is, so y is equal to 0 and C1 dot cos 0 into root over P by EI, which is cos 0 plus C2 sine again 0 into root over P by EI, that is sine 0. So you know the cos 0 is 1 and sine 0 is 0. So this is C1 into 1 plus C2 into 0. So this becomes 0. C1 is equal to 0. You get C1 is equal to 0. This is equation 2. So he put the second boundary condition at Bx is equal to A and Y is equal to 0. So we substitute these values in the equation 1. So 0 is equal to getting C1 cos L into root over Pi plus C2 sin L into root over Pi. So that means this becomes 0, C1 is 0, that's why this becomes 0 plus C2 sin L into root over Pi by E. So now C2 sin L into root over P by EI is equal to 0. So from here we can see either C2 is equal to 0, C2 is equal to 0 or sin L into root over Pi, P by EI is equal to 0. So at C1 is equal to 0, we already calculated C1 is equal to 0. Then if C2 is also equal to 0, then from equation 1 we will get y is equal to 0. Yes or no? So which means that the bending of the column will be 0 or the column will not bend at all. But this is not true. There is a deflection in the column. Then that means sine L root over of P by EI is equal to 0. So C2 cannot be 0. So then if sine L into root over of P by EI is equal to 0, so it may be sine 0 or sine pi or sine 2 pi. So this a root over of p by ei, I am writing this 0. It may be sine 0 is 0 or sine pi is 0 like that. So this L root over of p by ei is equal to 0 or pi 2. We take the least practical value, n root over p by ei is equal to pi. So now you can calculate p is equal to pi square ei by L square. So from here we are getting the value P as per the Euler's critical load. So now what is the formula? Euler's formula to calculate the critical load for the column and strut. So PE is equal to pi square EI by LE square. So what is PE? This is Euler's critical load. E is modulus of elasticity. I is least moment of inertia of the section of the column. This is important. I is least moment of inertia of section of the column and LE is equivalent length of the strut. Now what is this equivalent length of the strut? That we need to understand. So based on the end conditions, we need to find out equivalent length. See, as I told, there are 4 end conditions we are considering from the analysis point of view. One is both end pin jointed or hinged. So here the end A and B is pin jointed, pinned or hinged. The second one is one end is fixed and other end is free. Third one is one end is fixed and other end is hinged or pin jointed. The fourth end condition is both end fixed. So the A and B both end are fixed. So what is then here we can understand what is equivalent length. So equivalent length is nothing but the distance between the adjacent points of inflection. It's called equivalent length. So here in case of both ends are jointed or hinged, so if you apply the load, there is a deflection in the beam and the sign of moment changed from this point A and B. So this is the distance between point of inflection. What is point of inflection? Where the direction of the movement changed. So here The second case, because of this load, there is a deflection, and if you complete this, you'll find the point of inflection somewhere here. So the distance of the between the point of inflection is LE. So for both end hinged, the LE is equal to L. So for both one end fixed and other end free, your equivalent length LE is equal to 2L. Similarly, for one end fixed and the other end pin jointed, here you see when due to this axial compressive load, from here it goes like this, but after a certain point there is a change of axis. Okay, so from here to this end distance is called LE. That is nothing but 0.7 L. And for both end are fixed, the point of inflection comes at here, and LE is equal to 0.5 into L. So you need to just put this equivalent length value in that formula. So here is the crippling load as per the end conditions. Remember this. For both end hinged, your equivalent length is equal to L. For both one end fixed and other end free, your L is 2L. For both end fixed, your L is L by 2. And one end fixed and other end hinged, your LE is L by 2. So if you use these values of LE in the crippling load formula, pi square E by L square is coming pi square E by L square. Here it is pi square E by 2L square because LE is equal to 2L. So I'm getting pi square E I by 4L square. So this one is pi square E by L by 2 square. So I'm getting this value. And when you put the L by root 2 instead of equivalent length, you'll get this value. So this 4 is very, very important. You need to remember this equivalent length, the relation between the equivalent length and the actual length based on their end conditions. Now coming to slenderness ratio. So what is slenderness ratio? So we know the Euler's equation already, PE is equal to pi square EI by LE square. So the buckling of the column under the crippling load will take place about the axis of least resistance. What does it mean? Suppose there is a column, the dimension is in such a way that, so in which direction the buckling occurs means it will occur when about the axis of least resistance. Now tell me, what is the axis of least resistance here? If we draw the CG like this, and if I keep it like this and you draw the CG, definitely here there is a lot of material is there, so to resist the buckling load. But if I do like this, because of less material is available to tackle the buckling load, your buckling failure occurs in this direction. Means it may buckle in this direction, not in this direction. Okay. So buckling of the column occurs always about the axis of least resistance. So if that's so, so you need to substitute I is equal to AK square. What is A? A is area and K is least radius of gyration. Because the buckling occurs to the axis of the least resistance. So K is least radius of gyration. Then if we put that value in the equation, P is equal to pi square E. Instead of I, we will use AK square divided by LE square. Then pi square EA by LE by K whole square. So this LE by K is nothing but this is your slenderness ratio. I hope you understood. Now coming to limitation of the Euler's formula. So we know the Euler's equation that PE is equal to pi square EI by LE by K whole square. So LE by K is nothing but your slender ratio. So what is Euler's crippling stress then? You know stress is equal to load by area. So Euler's crippling stress is equal to E by A, or PE by A. So P is nothing but pi square E by A divided by LE by K square and A. So A cancels out. It is pi square E by LE by K whole square. So from this equation, you can see the crippling stress will be high. This crippling stress will be high when the slenderness ratio is small. So this crippling stress is related to the slenderness ratio. So what are the limitations then? So if we explain, if you understand by using this uh, numerical. So consider a mild steel of column with crossing stress is 320 Newton per mm square. And Young's modulus is given E is equal to 200 gigapascal. So now if we getting the crippling stress and crossing stress, your crossing stress is 320. So crossing stress is nothing but your crippling stress here. So pi square E by LE by K whole square. We put the value of E and we get the value LE by K is equal to 78.5 or 80, which means if the slenderness ratio is less than 80, so the Euler's formula for this mild steel column is not valid. Yes or no? If we use a slenderness ratio less than 80, so this value will increase, but at no point your crippling stress will be greater than the crossing stress. Okay, so that means if the value slenderness value is less than 80, so this Euler's crippling load formula is not valid for that. Okay, that is the limitation of the Euler's formula. It means it is only applicable for the very long columns. Okay, so to address these limitations of the Euler's crippling load formula, so there is this mathematician again Rankines developed one equation. That is 1 by P is equal to 1 by PC plus 1 by P. So he said, why can we only consider this crippling load? We have to consider both crossing load and crippling load, and you form a common formula where this crossing load and crippling load both can be applicable, and this formula can be used to solve all kind of columns. It may be short column, it may be medium column, or it may be long column. So he formulated this equation 1 by P is equal to 1 by PC plus 1 by PE. So P is nothing but your crippling load by Rankine's formula. PC is your crossing load, that is sigma C into A. Sigma C is nothing but your ultimate crossing stress. A is cross-sectional area. PE is the crippling load by Euler's formula, which is pi square EI by LE square, in which LE is effective length. We already discussed about this. So what he is saying, according to Rankine, if the column is short, which means the value of LE is small. Yes or no? If the column is short, then the equivalent length, your LE is small. Then if LE is small, so the value of PE would be large. Yes or no? If we put the value of LE here, we know PE is equal to pi square EI by LE square. If this is a small value, we'll get a large value for PE. Yes or no? If PE is large, then 1 by PE would be very small. Yes or no? So this 1 by PE will be small and may be negligible as compared to 1 by PC. So if we neglect this 1 by PE in equation 1, we get 1 by P is equal to 1 by PC, or P is equal to PC. So what Rankine says, so in case of short column, this 1 by PE can be neglected, and this is directly P is directly PC, that is the load, crossing load. So that means the column fails due to crossing load. So if you consider the second case, if the column is long, which means the value of LE is large. Yes or no? If the column is long, the value of LE large. If the value of LE large, then PE is small, because PE is equal to pi square EI by LE square. If this value is large, so we get PE is small value. If PE is small, then 1 by PE will be large enough compared to 1 by PC. Hence, the value of PC may be neglected in the equation. So, in case of long column, 1 by P is equal to 1 by PE. And hence, the P is equal to PE. So, here, in case of long column, so the buckling failure occurs due to bending. There is no failure due to crossing. Or we can neglect that because of the very small compared to this PE. So hence the Rankine formula can be written 1 by P is equal to 1 by PC plus 1 by PE, which gives satisfactory result for all length of the column, ranging from short to long columns. So if you solve this now, 1 by P is equal to 1 by PC plus 1 by PE, if you add these two, we'll get PC into PE, which is PE is coming here plus PC. So if you take the reciprocal of this, 1 by P is equal to this. So now P is equal to PC into PE by PE plus PC. So if you divide both the sides by PE, so this becomes PC by 1 plus PC by PE. Dividing the numerator and denominator by PE. So this sigma C into A divided by 1 plus sigma C into A by pi square EI by LE square. So we know I is equal to 18 square and K is least radius of gyration. If we put this value instead of I, we are getting this equation. This sigma C into A divided by 1 plus sigma 0 pi square E into LE by K square. So if we write sigma C by pi square E as A, so your equation becomes E is equal to sigma C A divided by 1 plus A into LE by K square. So this is your Rankine's formula for calculating critical load of columns. I hope you understood this. So next class we'll discuss about some applications of the Euler's formula and application of the Rankine's formula, so that we will get to understand how we can predict the buckling failure with different kind of cross sections, different orientations, different end conditions of the collapse. Thank you.